Okay, let's dive right into this explainer because we need to talk about how examiners set a highly calculated, literally a three-move trap for Cambridge AS and A-level physics students. Look, if you're sitting for the 9702 syllabus, you already know the margin for error is incredibly slim. Every single mark matters. So today, we're going to expose exactly how test makers use non-uniform motion to catch you completely off guard and force you to drop those critical marks.
So, why do students consistently lose marks on these scenarios before even realizing they've made a mistake? I mean, we've all been there, right? You walk out of the exam hall feeling super confident, completely unaware that the examiner just checkmated your grade. It's a massive confidence shock when results day rolls around. But don't worry, we're deconstructing this trap right here, right now. By the time we're done, you'll know exactly how to anticipate their every move.
This source material for this actually comes straight from the Cambridge Principal Examiner reports, and they state explicitly, no sugarcoating, that non-uniform motion is one of the most misunderstood areas in all of physics, mostly because, well, the forces involved are constantly shifting. But hey, here is the good news. We are going to fix this misunderstanding today by showing you exactly what Cambridge examiners are actually looking for when they grade your paper. We're handing you the framework to turn this exact weakness into your absolute biggest competitive advantage.
So let's jump straight into Section 1, the rules of the game and our core principles. Okay, so non-uniform motion isn't just your basic run-of-the-mill acceleration. We're talking about motion that involves frictional forces, drag or air resistance, and of course, terminal velocity. Picture a skydiver in free fall yanking open a parachute. That velocity violently shifts because massive air resistance is suddenly fighting gravity. The syllabus hammers home that top-performing students have a connected, conceptual grasp of these dynamic forces. You can't just memorize a textbook definition. You have to really understand how a falling object's acceleration drops as air resistance climbs right up until it hits terminal velocity. You've got to be able to take that concept and instantly apply it to completely unfamiliar, super complex situations.
And here's the thing about the exam. It prioritizes analytical depth and logical, structured reasoning way over just superficial breadth. The assessment objectives are pretty clear. Yeah, they want knowledge and understanding, obviously, but they put a massive weight on application and analytical depth. If you try to just cast a wide net and throw down a shallow, vague answer, you're going to lose the mark. The examiners are specifically hunting to see if you can construct a solid, evidence-based, logically structured argument.
Which brings us to Section 2, the winning methodology.
All right, the absolute crucial point here is mastering what we call the deconstruct, solve, evaluate framework. This is how you break down literally any non-uniform motion problem without losing your mind. Step 1, you deconstruct the given info. Identify your variables and figure out the exact scenario. Step 2, you solve it systematically, breaking the physics down into logical, bite-sized steps. And step 3, this is the one everyone skips, evaluate. Check your answer for reasonableness. Does that final terminal velocity actually make sense for the object they described? Stick to these 3 steps and you completely eliminate the panic from your problem solving.
And this right here brilliantly illustrates the method mark strategy. In Cambridge physics, having the correct final answer is honestly only a fraction of the battle. Examiners actually award marks for your process. You get points for accurately extracting data from texts and tables, for picking the right analytical framework, and for executing it with clear notation. Proper headings, correct terminology, the right formats, clear annotations, these are strictly required conventions. Seriously, if your final number is totally wrong, but your method is flawless and perfectly annotated, you can still salvage a ton of crucial points.
Now, in just a second, I'm going to share a really tightly guarded secret with you. It's the ultimate examiner clue that will completely change your terminal velocity answers. It is literally the difference between getting a top band score and completely bombing the question. But I had to give you that procedural framework first because it's going to make this upcoming clue so incredibly obvious.
Let's step directly into Section 3, Inside the Examiner's Mind. Listen to this warning directly from the principal examiners. The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. Guys, this is the ultimate danger zone. So many students memorize this perfect, beautiful textbook definition of drag or terminal velocity. They paste it onto their exam paper and boom, 0 marks. Why? Because they didn't apply it to the skydiver or the falling steel ball or whatever specific scenario was right there on the page. Rote memorization will completely fail you here. Application is everything. Going off those reports, here are the top 3 examiner warnings you absolutely must memorize. Number 1, answers are often way too vague. Examiners demand specific, scientific details. Number 2, forgetting format and presentation conventions. You've got to use the right formats and evaluate the data properly. And number 3, echoing what we literally just talked about, answers aren't specific to the context. If the question hands you a data table about a parachutist, your answer better reference the specific numbers from that exact table. So let's do a quick active learning exercise. I want you to create a memory hack for yourself right now. Invent a personal acronym to help you remember the factors that affect frictional forces: drag, air resistance, and terminal velocity. Think about velocity, surface area, fluid density, and shape. Come up with something catchy and lock that acronym in your brain right now. Having this customized mental checklist ensures you'll never ever forget to evaluate a crucial variable when you're sweating under exam time pressure. Moving on to Section 4, the interactive challenge, where we compare flawed versus improved answers. Okay, I actually want you to pause this explainer for a second. Mentally predict the fatal error that a typical student might make in a non-uniform motion comparison question. Think back to what we just went over about vague statements and lacking context. Do you have your prediction? All right, let's reveal the examiner's correction. Just look at how starkly these two approaches contrast. A flawed, generic student answer probably says something incredibly basic, like air resistance increases until it equals weight, which, okay, is technically true, but it's completely stripped of any context. Now compare that to the top-end's answer. This high-scoring approach seamlessly moves from concept to evidence to scientific reasoning, directly applied to the scenario. It uses comparative connectives. It points out similarities and differences using the actual data provided. It's just a wonderfully structured, completely airtight argument. So, why exactly does that comprehensive answer win? Because the top-scoring candidate is demonstrating deep evaluative thinking. They question assumptions. They consider different perspectives. But most importantly, they justify their decisions with hard evidence pulled directly from the texts or tables they were given. When they're asked to compare things, they don't just lazily list similarities. They meticulously identify similarities and differences, and then draw conclusions about their relative importance. That, my friends, is exactly how you secure full marks. But here's the catch. Mastering the written explanations of non-uniform motion is totally useless if you fall into the upcoming high-stakes graph analysis trap. This is the big unresolved problem. It's the final hurdle that catches even the smartest students. Analyzing non-uniform motion curves, calculating changing gradients for acceleration, figuring out the area under the curve when drag is involved, it all requires a completely different tactical approach. If you don't know the checkmate move for these graphs, all your hard work on the theory is going to go completely unrewarded. To make absolutely sure you don't fall into that trap, you need the final piece of the puzzle. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. The checkmate move is waiting for you in our next explainer, where we walk through the exact past paper graph skills you need. Until then, I want you to ask yourself this. If a graph shows an object reaching terminal velocity, what exactly is happening to the area under that curve as time stretches on? Think about it, and let's secure your top grade together.